Welcome. In this video, we're going to switch gears a little bit and talk about some geometry. And while, these trigonometry topics that we're going to explore here the rest of the way through are not really part of Texas Algebra 2, I feel like it's something that's really important for students that are leaving Algebra 2 to be familiar with. Okay, and the reason I feel that way is that, either you're going on with me to pre-cal next year, and you're going to be studying a lot of trigonometry, or you're not, but you're probably going to be taking the SAT or ACT, and we need you to have a little bit of trigonometry so you can do the best you can on those two. Okay, so we're going to start off with where I think trigonometry should start, the special right triangles. So the first special right triangle we're going to look at is the 45, 45, 90 triangle. And so this comes up with, we start with a perfect square, right? And then we cut it in half diagonally. It's look something like that. Okay, and we're left with a triangle. Now, suppose just for now that this was a square with sides length 1. Okay? And we wanted to find the length of this diagonal. Okay? We could use the Pythagorean theorem to find that. We know that, the one leg squared plus the other leg squared is equal to the hypotenuse squared. So we could say, okay, 1 squared plus 1 squared, that's 1 plus 1. We know that's 2. And 2 could be equal to c squared when c was equal to the square root of 2. And we're going to only take the positive square root of 2 for now because we're only interested in triangles with positive side lengths. And so we see that c is going to be the square root of 2. But, I'm assuming that you've been through a geometry class and you've seen how triangles can be scaled up or scaled down, keeping their same shape. And so, might be interested in what if the legs had length x. And what we're going to find doing the same process is that c is going to be x times the square root of 2, right? Because we just scaled the square up, or this right triangle up by x units. But I think it's good for us to go through the algebra again. Right, we can set up the Pythagorean theorem, try to solve for c, and do a little bit of simplifying on radicals, and I'd say, square root of x squared is equal to x, because we're assuming x is a positive side length. Okay, really the square root of x squared is the absolute value of x. But if we've got these things, then we can go in and we can say that for a 45, 45, 90 triangle, if we have side lengths that are both x, the hypotenuse is going to be square root of 2 times x. So, for example, I could show you a triangle like this and be like, okay, here's this, find the value of x. Right, so if we know that it's a 45, 45, 90 triangle, which we are seeing, I guess it's not explicit that that's a right angle, but in this discussion it's always going to be a right triangle. If we've got those two tick marks, it means it's the same length. So I know that this is going to be a 2 as well. And while we could use the Pythagorean theorem, knowing that the second leg is also equal to 2, then it would be faster to say that, okay, well, x is going to be equal to the square root of 2 multiplied by the length of one of the legs. Okay, so that's square root of 2 times 2. We usually write that as 2 root 2. Now the backwards version of this question would be like, okay, I'll give you the hypotenuse, find me the value of x. Okay, and so we would say, all right, I think that the way to go here is going to be set up an equation, right? Stick to what we know, is that the hypotenuse is equal to the square root of 2 multiplied by the length of one of the legs. And if the length of one of the legs is x, then we can say, all right, we could go from 4 back to x by dividing by the square root of 2. And we're also seeing that in the equation. So I'm going to divide both sides of this equation by the square root of 2 and get 4 over the square root of 2. And then, what was I thinking here? Oh yeah, we are going to need to rationalize the denominator. Because although that's probably a safe place for you to stop, if you're like, responding freely on a quiz or a test in my class, if it's multiple choice, the answer choices aren't going to be written like that. So we're going to multiply by a clever form of 1 to make sure we have a rationalized denominator. And we're going to say, all right, so that'll be 4 square root of 2, nothing we can do with that. But square root of 2 times square root of 2, that's 2, and we know how to divide by 4, or 4 by 2, and we'd say x is equal to 2 square root of 2. Now let's talk about the 30, 60, 90 triangle. So we're going to start the same idea. This time we're starting with a perfect triangle, an equilateral triangle. And then we're going to kind of cut it from one vertex along the opposite base perpendicularly, which, something you would have learned in geometry is that that's going to bisect this. Okay, so those two things are equal. And so that means that if we've got, side lengths, hold on, what do I want to say? Okay, I'm going to call this, I'm going to actually say that this is length 1 for now. Okay, and so that would mean that this is also 1 and each of these lengths of the triangle were 2. Okay. So if I went out and just took, say, it looks like the top half of the triangle and just looked at it on its own, I could say, all right, well, I know that that 2 is there because it's like, that's the same side. And then the short leg is, well, that's going to be 1 right here. And then I could be interested in the value of this other leg. Maybe I'll call that B. And then I'm going to go through, Pythagorean theorem, just look at it with the 45, 45, 90, and figure out what the value of B is. And then I'll say, okay, what if I had X? All right, so I would say 1 squared plus B squared. Okay, that's going to equal 2 squared. And then I'm going to say, all right, that's 1 plus B squared equals 4. So B squared equals 3. And B is going to be the square root of 3. So in this situation, we have this 1, 2 square root of 3 pattern. And it's going to be the same as that 1, 1 square root of 2 pattern with 45, 45, 90. If we go and, think about this in terms of just x, then we're generally going to say that x is going to be the shorter leg. It's going to be the leg that's across from the 30-degree angle. Okay. I didn't even label it on the other one that both of those were 45. I guess I just thought it was self-evident since the 2 legs were equal, the 2 angles would be equal, but I guess you don't really necessarily know that yet. Okay. And then, so if that one's 30, then this one's going to be 60. Okay. And so if the one across from the 30-degree angle, the short leg, is x, then the hypotenuse is going to be 2 times x, really because of this diagram off on the left, where now I'm thinking about, x and 2x. Okay, I could do the same thing. Call the long leg B, set up the Pythagorean theorem, run through all of that, and you'll see it works really very similarly to how it went when we did the same thing on the 45, 45, 90, but we'll see that B is the square root of 3 times x. So in general, if we've got the short leg of a 30, 60, 90 triangle, we know the hypotenuse is twice the short leg, and we know that the longer leg is the square root of 3 times the shorter leg. But before I move on to work a couple of examples of this, I just want to address a somewhat common misunderstanding that I've seen come up before when I've taught pre-cal. And so I'm only going to tell you what's true. Okay, the square root of 3 is a number that's less than 2. And I'm going to be able to convince you of this without going to a calculator, right? I need you to know that, though, that the square root of 3 is going to be a number that's less than 2, because it would be easy to think that the hypotenuse was the one we multiplied by the square root of 3 if we thought the square root of 3 was the bigger number, because we know that the hypotenuse is the longest leg of a triangle, or at least of a right triangle. So the reason that the square root of 3 is less than 2 is that 2 is the square root of 4. Okay? And we know somehow, just like very deep in our knowledge about arithmetic and square root and stuff, that you get a bigger square root by taking the square root of a bigger number. Okay, so I just want to make sure that you're good with me that the square root of 3 is a number that's less than 2. All right, now for example, find the values of x and y. Okay, we've got a 30, 60, 90 triangle. I guess we would really know that if we had the little right angle indicator there. We've got a 30, 60, 90 triangle, and the length of the shorter leg, the one across from 30, is 12. So we know that to get to the hypotenuse from the square root of 12, that would be y, and we're going to double it. Okay, so y is going to be 2 times the square root of 12. And, I guess we could write that in simplified radical form, even if they didn't give it to us that way. We could say the square root of 12 is the square root of 4 times the square root of 3. Okay, the square root of 4 is 2. Okay, that would go with that other 2 and make 4 square root of 3. And then to get x, okay, to go from the short leg to the longer leg, we're going to multiply by square root of 3. So x equals square root of 3 times square root of 12. And I'm just going to combine those. It's going to be the square root of 36, and that would just be 6. So it's a pretty typical problem type, make you practice your simplified radical form, do a little bit of geometry, and so let's try another one. Okay. I think this one would be a good one for you to try on your own. One where you're given the hypotenuse. The one where you're given the longer leg, they can be a little tricky, so I might show you me doing that. But why don't you try to find the values of x and y? So you're going to do that. Make sure you pause the video because the answer is just going to pop up. All right, there you go. So me personally, I'm always going to like set up an equation. Now, if you're saying that, okay, to go from the short leg to the hypotenuse, I multiply 2. So to go from the hypotenuse to the short leg, I need to divide by 2. Okay, that makes a lot of sense. Okay, that's the thing. But really what you're doing there is just doing that algebra that I showed in green in your head. Okay, so if we're saying 10 is 2 times x, and we say, okay, x is 10 divided by 2, and we see that x is 5. And then to get to y, you kind of want to use the short leg. Okay, I don't think it's worth memorizing like the conversion factor from the hypotenuse to the short leg. Why do it? I guess you would divide by 2 and then multiply by the square root of 3. Okay, but what we can do is we can just set up an equation, right? Y is equal to the square root of 3 times x, because the longer leg of a 30, 60, 90 triangle, its length is the square root of 3 times the length of the shorter leg. And so we could say y is square root of 3 times x. We just found out that x is 5, so we know that y is 5 root 3. Now the last example I've got for you, this one's a little trickier, okay, where they give you the longer leg and they ask you for the other two. Okay, so what I want to do is find the value of the shorter leg first, okay, because I've got the longer leg and that's 5, that leg that's across in the 60-degree angle. So what I know is to get the longer leg, I take the shorter leg and I multiply it by the square root of 3. I could say square root of 3 times x, it doesn't matter, right? So we can divide both sides by square root of 3 and say x is 5 divided by square root of 3, but we want to write that simplified radical form. So we multiply it like this, and we'd say 5 square root of 3 divided by 3. And then if we were interested in the hypotenuse, that's where we get the hypotenuse by doubling the short leg, so that's going to be 2 times x, which is going to be 2 times 5 root 3 over 3. And we could look at that like 2 over 1 times 5 root 3 over 3. We're going to get 10 root 3 over 3. Now maybe I'll say y equals 10 square root 3 divided by 3. Okay, that's all the examples I got for you for this video. Thanks for watching.